All right, well, welcome to week 3. We are now officially 1/6 of the way done with the quarter. Love it. Love how fast this flies. And we're basically going to pick up where we left off. We're going to talk a little bit more about applying vector value functions to physics. But then we're going to move on to the next chapter. And today we're going to talk about multiple integrals. Give you an idea of what that actually means. Because it turns out that there are, just like we've got single integrals, you've got double integrals, you've got triple integrals, you've got as many as you want. So we'll start getting into that, talk about what it means, what they do, and the like. But before we go there, any questions on the homework? Anything out there that we need to discuss?
Bruce, did you remember to update the 3.4 due date?
I believe so.
Cool.
I'm pretty sure that I did it, but y'all can double check. But I believe that I did get that extended. So
Yeah, I just looked. You did.
okay, cool. I guess for a absent-minded professor, there are still times I'm not completely absent-minded, so I'll take it. Okay, so then Evan, you said you want to look at number 10 from 3.4. We can definitely do that. Any other ones out there that people want to see? Okay, well then let's go do that. I will share my screen here and then we'll go take a look at that one. All right. So hopefully you all can see my screen. Hopefully it decides to show me the homework. There it comes. One of these days I'll break down and buy a new computer. I'd rather spend my money on high quality reader. All right, finally. So let's go take a look at question number 10 here. All right, so it says we want to find the tangential and normal components of the acceleration for this curve at the point t equals 2. All right, so this is definitely something that we saw last time, right? I called these components the AT and the AN. So the portion that's tangential and the portion that is normal. Okay, so how are we going to go about doing this? What's the process?
First, find the acceleration.
Okay, I think that's a great idea. Let's actually find what the acceleration is. So we're going to be able to do that by differentiating it twice, right? And then probably what we want to do is just go to getting the components. And we developed some rules for those, or a process for that last time. So let me stop sharing this and let's go put on a whiteboard. And we'll start working the sucker out. All right, so let me go ahead and first put down what R here is. So we've got R is equal to minus 5t cubed 2t to the 5th. And again, we're going to be looking at t equals 2. So let's get our velocity. Velocity is the derivative of this. That's minus 5, 15t squared, 10t to the 4th. And then the acceleration is the derivative of that. So 0, 30t, 40t cubed. So at t equals 2, let's just go ahead and get what all these things are. just so we've got them. The position is minus 10, not 80, about 40. And let's see, 32 times 2 is 64. Okay, so there's our position. So we're way out there. I'm writing like a 3-year-old today. Apologize for that. Okay, so then the velocity at that point is minus 560, and then 160. And then the acceleration is 0, 60, 320. All right, so there's our R, V, and A. Cool. So how are we going to find these? Which is easier to find, the AT or the AN?
AT.
All right, so why AT? Why is that a little bit easier? Yeah, I agree, Victor. You just put in the chat box dot product. When you want to find AT, then what you can use is the dot product as opposed to the cross product. So what is it that we dot to find AT? Like, what's the formula? Do you guys remember? So Victor just put in the chat box, V dotted with A divided by the magnitude of V. What do you guys think? Does that sound right?
Yeah, sounds right.
Yeah. Okay. Well, we've got V, we got A, so we can go ahead and dot those. V dotted with A is going to be 0 plus, oops, there's no bracket there, 0 plus 360 plus 16 times 32 is 512. Throw on a couple of zeros. So V dotted with A then would be 51, 560. And then we need to divide by the magnitude of V. So let me just, yeah, I'll do that right here. So the magnitude of V then is the square root of minus 5 squared plus 60 squared plus 160 squared. Right, so just using those. So then we know that A sub t is going to be 51, 560 divided by the square root of all that nonsense. So what is that? 25 plus 3,600 plus, let's see, 16 squared is 256. Throw on a couple zeros. And I'll let you, get a number for that because I'm not too concerned about the actual value. All right, so there's AT. Any questions on that part before we go to AN? Okay, so now that we've got AT, how are we going to get AN? All right, so Victor just put something in the box. Let me just remind you there are 2 ways of finding AN. We can go back to the kind of how it got derived and everything, and that involves a cross product. It's V cross A, the magnitude of V cross A, divided by the magnitude of V. But I don't recommend doing that one because doing the cross product, like if you would look at these and doing the cross product of that's going to be pretty gnarly and finding its magnitude and everything. So instead, what you can do is kind of what Victor put in the chat box. It's not quite right, but he was close. That A sub n, the magnitude here, using the Pythagorean theorem, it's going to be the magnitude of A squared minus the magnitude of AT squared, right? Which I guess magnitude of AT That is my AT, because this isn't a vector, this is just a component of it. But it's just using the Pythagorean theorem. So this is what I would recommend using in this case, because we already just calculated AT, that's this right here. And then the magnitude of A, since we know what vector A was, we can go ahead and get its magnitude and square it, and then do that subtraction and take the square root. I'm not going to bother going through it with the numbers here, just because there's no point in wasting everybody's time, because I think you all see what you need to do, just using those guys. All right, so Victor, is there a way to find the unit normal vector knowing A sub n? Yes. If you know, well, okay. When you say knowing A sub n, do you mean the entirety of the normal component of the vector, or just its magnitude? Okay. So if you know its magnitude, that's not quite enough. If you know both magnitudes of AT and AN, then it is possible. But it's a little bit tricky because it's basically going to give you a system of equations as you're trying to find the various components. But if you know the entirety of the vector, if you know the entirety of the normal vector portion, you can just get its magnitude, divide out by that magnitude, and that would give you your n. Does that answer your question, Orion? Yep. Okay, cool. All right, any other questions specifically about this problem or any other homeworks that we want to look at? Just real quick, because that was you, Evan, right, who asked for this. Was this clear enough? You kind of see where you need to go? Yep, okay, good.
I have a quick question about motion in space.
Okay, go for it.
So in the textbook I got, it gives an example of Kepler's law of planetary motion,
Yes.
and I didn't quite understand it.
Okay.
You don't have to go into great detail, but
Well, that's something that I was going to talk about today a little bit more when we talk about physics of space. And I don't mean outer space, I mean 3D. But I was going to talk about Kepler's laws, and a little bit about how they are formulated and all that. So I bet I will answer that question later today. If I don't, please let me know. And I'll come
sure.
back to it. Okay, cool. All right, so any other questions before we head over to the whiteboard? All right, well, I'm gonna go switch over there, so I will see you guys in just 1 second. All right, so let's talk a little bit more physics, some more of the things that we did before, and kind of apply it to some other ideas. So last time we just did some generic, hey, here's some path, let's find tangential normal accelerations and all that. But what I want to do today is some specific examples. And the first one I want to talk about is free fall. All right, or projectile motion is another name that we use for it. So let me just call it that. All right, so projectile motion. This is a situation where only gravity is involved. And my pen is dying out. Hold on, let me switch it. So the only force is gravity. All right, now, again, I don't know how much you guys know about physics. Some of you I know more than others, but just let me just sort of back up and say then, if we're going to be looking at only gravity, the acceleration vector is going to be pointing only in the negative y direction or the negative z direction. But we're going to assume that this is two-dimensional. And so the acceleration is going to be given by 0, negative g. So the y component will be up and down like we're used to. And the x component will just be in the direction of travel. And even if this particle is moving at some weird angle, we can just be in line with that angle, and then we're moving two-dimensionally. This might start you thinking though, okay, but what about say like a baseball or something that's got a curve to it, right? That's coming and kind of bends. That kind of motion is not projectile motion because there are other forces involved. Specifically in that case, it's drag, right? It's frictional forces with the atmosphere. So if all we have is gravity, we can treat it as two-dimensional. Now, this isn't necessarily the best, especially on Earth, because we do have other things that are going to impact objects just traveling through the air, specifically air resistance, drag, friction. But if we were to go somewhere else, like onto the surface of the moon, surface of Mercury, other places like that where there is no atmosphere, then this is going to totally work. And that's why I also want to leave it as just negative g. I don't want to actually attach a number to it just yet, because we want that to be able to change. Like on Earth, in general, gravity is on the surface of the Earth, it's 9.8 meters per second squared. But even that varies. You go to the top of Mount Everest, you get a different gravitational constant than you would at, say, Death Valley. Or gravitational acceleration, I should say, that the gravitational constant is always, but the acceleration will be different. But it also changes at different places on the Earth due to latitude. Turns out that if you're at the equator, the gravitational acceleration is less than if you're up at the pole. Not by a lot, but by a little bit. So even that, treating this as constant is maybe not the best thing to do, especially if we're talking long distances. But we're going to go with it. Okay, we're just going to start with this. Okay, so here's my goal then, is I want to get a function for velocity and for position. And then we'll break it down and do the same sort of thing where we look at, okay, what part of this acceleration is tangential? What part of it is normal? So we can look at how speed is changing and the like. Now, again, spoiler alert, most of you already know this. The shape that we get with this is parabola. It's going to be a parabolic path. So you already know that. You know that the speed is going to change, right? As an object falls, it speeds up, again, in the absence of air resistance. With air resistance, we eventually reach what we call terminal velocity, which is where it gets balanced out. You'll talk a lot about that in spring, in differential equations. We're going to give you the tools to deal with air resistance, just to make it, so that we can actually attack something a little bit more realistically, right? But anyway, so let's go ahead and find all this stuff. So we'll start with v, right? So v is the integral of the acceleration with respect to t. So we saw with vector value functions, it's just a matter of integrating each piece separately. So we're going to get 0, minus gt. But then we're going to add to that a constant vector. And for this, what I'm going to call that constant vector is v naught. So that's going to be the initial velocity. The little sub-zero just as a way of describing it as beginning, right? We say naught, N-A-U-G-H-T. V naught or v sub 0. So that's going to be our initial velocity. If you want, I don't really care. I tend not to want to do this just because stuff gets kind of cluttered. You can consider v naught as components, say, v x naught, vy naught. So basically just saying there's initial x velocity and initial y velocity. And those are there. All right, but I'm just going to leave it as this plus v naught because, yeah, why not? We'll just leave it that way. All right, so there's going to be our velocity vector, which then means if we want to get our position vector, we just have to integrate again. We're going to integrate the v this time. So if we integrate this thing with respect to t, all right, well, again, we're going to get a 0, a minus gt squared over 2. This v naught, it's a constant. It's a constant vector, which means that constant goes along for the ride as we integrate. So I'm going to be able to write here just v naught times t. And then I have to add another constant. But that constant vector, I'm going to call it r naught. And just like v naught was our initial position, r naught is going to be our, v naught was our initial velocity, r naught is our initial position. So we started with an acceleration that was just 0, negative g. It gives us a velocity right here, which then gives us a position here. So every free fall problem is done. Yay. Right, this is where when we get that intersection of math and physics, it's great because the mathematicians are all about let's just do things one time. Well, there you go, physicists. Anytime you want to do any kind of free fall, this is it. Doesn't matter where you are. Go to Mars, okay, insert a different G. Instead of throwing it straight up, I'm going to throw it at an angle. Okay, well, you just changed your V naught. Give me a different V naught. Okay, I'll plug it in, whatever. Started at a different place. I don't care, right? So notice that all we need to know in order to do this is where it starts, what kind of velocity it has at the beginning, and what's our gravitational acceleration. So you put in those three things and you've got your answer for position. So kind of nice, right? I mean, it's pretty quick and pretty easy, but there it is. All right, so let's talk a little bit about the A sub t's and the A sub n's and the like. Okay, so first of all, notice that the speed is changing because this component, this portion of the velocity vector has t in it. So the speed of the object is changing, which tells us that there should be an A sub t. A sub t was the part that changed the speed. The direction is also changing. You can see that down here. So we should expect that there should be an A sub n as well. So let's find them. Let's find those different values. Now I'm going to move over to this side of the board. If the glare is such that you can't read it, throw something up in the chat box, say something out loud so I hear you. Let me know and I will adjust where I am, okay? So, because I noticed that in my screen there's a bit of a glare like right over here. Okay, well, let's see if we can calculate the A sub n. So we're going to want to do what we did before for the A sub t. We're going to do v dot a divided by the magnitude of v. All right, so the v dot a we're actually ready to do. You'll notice that this is going to be 0 dotted with whatever this thing gives us. That doesn't really matter, so that 0 is gone. But then we're going to get a minus g. So negative g times negative gt. And I'm going to put the plus v y sub 0 because it does matter what that initial component was for us to get v dotted with a. And then we're going to divide by the magnitude of v. Well, the magnitude of this vector is going to be the square root of vx naught squared, because that's the x component, plus vy naught minus gt quantity squared. All right, let's simplify this just a very little bit. If I distribute through the top, I'm going to get g squared t plus g times, or sorry, not plus, minus g times vy naught. So that's on the top. And then on the bottom, if I were to square everything out, I'm going to get a vx naught squared plus v naught or vy naught squared. So that's just the square of the speed. But then there's also going to be minus 2 vy naught gt plus g squared t squared. But there's our a sub t. And so you see that there is going to be some sort of tangential acceleration always. But there it is. There's the formula for it. All right, so then for a sub n, we'll go ahead and do a sub n. And we'll do it the same way that Victor suggested we do the one on the homework, which is let's look at it as the square root of the magnitude of a minus at squared. Because we know the magnitude of a. That's actually really easy. That's just g. So we're going to get g squared minus this thing squared. Okay, well, that's going to be g squared times t minus vy naught, gt minus vy naught squared, divided by all of that stuff. We can get rid of the square root now. So I just literally just copied all of this that was in the square root, and I took the square root off of it.
Wait, I'm kind of confused, Bruce.
Sure. Where did I lose you?
That the last expression.
This down here?
Yes.
Okay. So what I'm doing is I'm squaring the one we found for AT.
Okay, because it's these.
Because we're using the Pythagorean theorem, and so I have to subtract the square of this.
Okay, so is that quantity being divided under a square root or no?
No, not anymore. Because when I square the bottom, squaring the square root makes that square root go away. I mean, it is part of the big square root.
Oh, it's a part of the big square root.
Yeah. Because this fraction is just the AT squared.
Gotcha.
All right, so again, you can do some magic on it to simplify it a little bit, right? Get a common denominator, cancel stuff. There's a g that you can factor out because of the g squared, yada, 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 right? So you can simplify it down, but there's your a sub n. Again, notice that it is not 0. It does depend upon t. And so depending upon where we are, at what point in the curve this magnitude will change. And it just really depends on where we are.
So in the denominator of a sub t,
Yeah,
is that vx naught squared plus vy naught squared?
yes.
Okay, just making sure.
All right, so again, the moral of the story here is we've now done this for every single projectile motion problem. Done. Again, it's not rocket science, right? All right, so let's actually do one. Let's look at a specific example so you can see how we would go about doing this, and then we can look at some specific n's and t's and a sub n's and a sub t's and see how everything falls out. All right, so let's say that we're going to be firing something at an angle of pi over 4 radians. Most books would say 45 degrees, but we don't play that. So we're going to go off at 45 degrees, so pi over 4 radians. And let's say that the initial speed equals 20 meters per second. Okay, so we're going to toss it at an angle of pi over 4 with an initial speed of 20 meters per second. And I'll even tell you that we're up on top of a building and that this building is 30 meters tall. So here's what I want to do. I want to get an R. I want to get a position function. So that's going to be the first thing we're going to do. We're going to find R of t. And then we're going to find a sub t and a sub n at a couple of different places. So at the start, so when we first toss it, I want to see what is our a sub t and a sub n. And let's find those same things at the top of the path. And then the last thing I want to find is what's the speed right before impact. Because we know that it is going to follow a parabolic path, right? It's going to do something like this. And so right at this instant, right as it's about to hit the ground, I want to know what's its speed. All right, so I gave you everything you need. Well, with the exception of one thing. What didn't I tell you that I just kind of assumed that we would know?
G.
Yeah, gravity, right? The fact that we're actually on Earth, right? Because remember, there were three things we need. We needed initial position, we needed an initial speed or initial velocity, and we needed G. Well, I gave you initial position. I told you where we are when we were through it. I gave you initial velocity at ish. I told you what direction and its speed, so that should be enough for us to find velocity, right? So the only other thing that was missing was G, but we'll go with that we're on Earth. We're not doing any kind of alien problem here just yet. So let's go with the assumption that G is 9.8 meters per second squared. So the time bit, so Victor, you just said, you know, time, the time doesn't actually, doesn't get affected here. I mean, we will have to calculate times to figure out where we are at different places. But basically, once we start that stopwatch, we're good to go. As soon as we hit go, time takes care of itself. All right, well, we already did all the work. So let me pop back over here. I already showed you that we can get our R by looking at, it's going to be 0 minus 1/2 gt squared plus v naught t plus r naught. So let's build the v naught t, or the v naught and the r naught, so we can put these together to get our vector. Okay, well, we'll put in g as well. So that's going to be 0, negative 4.9 t squared plus. All right, so how are we going to figure out the v naught? Well, let's think about this. I gave you a direction, and I also gave you a magnitude. So if you ever want to build a vector knowing direction and magnitude, you can actually multiply the magnitude by a unit vector. And the easiest way to build a unit vector, if we're talking about angles, is to use sine and cosine. Sine for your y, cosine for your x. So we're going to have 20 times cosine pi over 4 comma sine pi over 4. And I'm going to put plus times the t. Because this guy, cosine pi over 4, sine pi over 4, is a unit vector, because it's just coming from the unit circle. So I'm just multiplying it by 20. And then I need to add to that my initial position. Well, I need to designate coordinates then. I need to decide where 0, 0 is. And since I am the complete master of my coordinate system, I'm going to make 0, 0 be at the ground right below us when we toss it out. And so that way, my initial position vector is 0 plus 30. So I can go ahead and combine all of that. And we get r of t is equal to 0 plus 20 cosine of pi over 4 plus 0. Cosine of pi over 4 is root 2 over 2 times 20 is 10 root 2. That's times t. So there's the x component of my position vector. And then the y component is going to be minus 4.9 t squared plus 10 root 2t plus 30. So same deal, I'm just adding the respective pieces together.
So
for
you
those
just
who-
added the three different the 3 different vectors.
Yep, that's all I did. Because I know with vectors, I just add component by component and pieces them together. So for those of you who took your physics, this might look a little familiar. You probably did it separately. You probably looked at x component and then y component separately. But these are your two pieces. Like in the x direction, all it is the initial x velocity times t. Because there's nothing speeding it up or slowing it down horizontally. Right? The only force is gravity, which is pointing straight down. And with gravity, you get that parabola, the minus 4.9 t squared. The 10 root 2 t was the initial velocity, so v naught t. So initial y speed and then initial y position. Even if you've not taken physics, this one that's on the right, you might recognize because you saw that in like a pre-calc class somewhere when we were talking about parabolas. It's your minus 1/2 dt squared plus v naught t plus h naught or whatever, y naught It's that same piece. But notice that we can just lump it all together as a vector and be done with it in one step. That's kind of the power of vector value functions, is we can kind of integrate all this stuff into one thing and do it all at once. All right, so I'm going to put a check mark next to the first one, find R of t. We got it. Okay, so then it says, well, let's go ahead and find a sub t and a sub n at the start. So at the start, that's going to be t equals 0. So maybe let's look at the acceleration and the velocity and do kind of what we did just a minute ago. So we know that a of 0 is 0, negative 9.8. That's a always, right? We also know, we'll save a spot for v here in a second, but we know r of 0 was 0.30. That was our initial position. The initial velocity, that was that v naught, right? But v naught, that was 10 root 2, comma, 10 root 2. So there are 3 functions at time 0. So if we want to go ahead and calculate, say, a sub t, we'll go ahead and use that dot product thing again. So a sub t is equal to v dotted with a over the magnitude of v. Okay, so v dotted with a is going to be minus 98 root 2. And the magnitude of v, I'm not going to bother calculating it because I already know it. It was 20. I mean, if you want, do the Pythagorean theorem on this, that's fine. But how do I know it's 20? Without even calculating.
It's going to be the square root of 400.
Okay, it will be the square root of 400, which is 20. But it was what I gave you at the start. Right? I told you the initial speed was 20 meters per second. And speed is the magnitude of velocity. Oh, tricky. Tricky. All right, well, anyway, so this is minus 4.9 root 2, which is, yeah, whatever that is. It's going to be 7 something. Probably on the order of like 7.4, 7.3, I think. But it is what it is. All right, so at the very beginning, there is tangential acceleration. It's negative, which tells me that the speed is slowing down. Okay, well, a couple things. First of all, look at the picture. If it's negative, tangential is just going to be pointing in this direction. But it's negative, so it's pointing backward. So it is slowing down. But it's doing 2 things. It's kind of pulling back on it in the x direction and in the y direction. But that's because only acceleration is applying, is gravity. Only is gravity, and so some of that is slowing it down. But we know that. We know that it slows down, right? The vertical piece is dying out as it reaches the top, and then it starts to speed up. So at that instant, it shouldn't surprise us, but that's negative. Okay, well, so there's a sub t. So then a sub n. All right, well, a sub n, that's going to be the square root of a's magnitude squared. Well, a's magnitude was 9.8, so we'll have 9.8 squared minus 4.9 root 2 squared. All right, so that's going to end up being the square root of 9.8 squared minus 2 times 4.9 squared. And again, that's going to be whatever it is. It's going to be something on the order of like 7, I'm going to guess. That's a total ballpark, because I'm looking at this is about 5 squared, which is 25, times 2 is 50. This is about 100. 100 minus 50 is 50. Square root of that's around 7. It's a little bit lower. So it's probably like high 6 point something. But regardless, there's definitely an a sub n. So at that moment, at that one moment in time, as soon as we throw it, instantly gravity is working on doing both, slowing it down and making it change direction. But again, both of these make sense. Look at the picture. We know the path is changing, and we know that it's slowing down as it goes towards the top. Okay. Honestly, I think I'm just going to talk you through the other bits because I'm getting bored with this. And now we'll do the third one, and then we'll talk through the top, or number 4. So how do we find out a sub t and a sub n when we're at the top of the path? Because you all know where it is, right? It's the vertex up there. But how do we figure out a sub t and a sub n at that point?
Would we have to find the gradient of the position function?
Don't necessarily have to find a gradient, but I do want to use, well, I'm not going to use the position function, but we could. I think what you mean more instead of gradient is probably a like optimization thing, right? Try to find out where that position is highest. Is that what you meant?
Like the maximum or the minimum.
Okay, so we could definitely do that, and that is kind of what we're going to do. I saw that Victor put in there, we need to find time, right? And we do. We need to find the time when we're up at that point, so we can plug that time into these functions, and then therefore find a sub t and a sub n. So let's think about it from what Bradley said. He was like, well, how about if we try to maximize? And what we're trying to maximize is the height. Right? It's the y. So it turns out we could just go straight to that and just do the calculus on that piece. So if you were to differentiate that with respect to time, you're going to get minus 9.8t plus 10 root 2. And we know from Calc 1 or wherever it was that you take the derivative, you set it equal to 0 to get your time. And so time is going to be 10 root 2 over 9.8. So that's the time when we're at the top of the path. And so what we would do at this point then is plug this in to our acceleration, our velocity, and use that to figure out the different pieces.
Bruce, so you're taking the derivative of the position function of the y value.
Yep.
And setting that to 0, why exactly?
Because I'm trying to maximize y. I want to find out when my y is biggest.
When the derivative is 0. Okay, gotcha.
Right, and from Calc 1, yeah, we know that critical points occur where the derivative is 0 or undefined. Obviously, this derivative will always be defined, so the only option then is to set it equal to 0. It turns out that this is also just the y component of velocity. So alternatively, we could have looked at the y component of velocity and seen when it is 0, because at that instant, when it gets to the top, the y velocity is now 0, because it was positive, and then it starts turning negative. And we know from like the intermediate value theorem or whatever that there has to be a place of 0 in between. So that's another option when it comes to finding that. But now, like I was saying, we can plug this t in to find our acceleration and velocity at that point, and then go through the process of calculating a sub t and a sub n. All right, now, kind of fun fact about this point, right? So here, it turns out that you're going to find that a sub t is actually equal to 0. And you're going to find that a sub n is equal to negative 9.8. I'll let you kind of play around with these and actually do that calculation. But what that means is that all of it is pointing normal. And this should make sense anyway, even if you don't run the numbers. Because think about this. Think about just acceleration. Only acceleration is gravity. Gravity is always pointing downwards, right? So wherever we are, here's our A vector. When we're at the top, that vector is normal to the path, right? It's going straight up and down. So all of that acceleration is in the normal position. So the numbers should, like when you run the numbers, you should get this anyway, but just logically, visually, looking at the graph, shows that we should find that. All right, so there's your a sub t and a sub n at the top of the path. So then lastly, when it says what is the speed right before impact, that's another one where we have to find t. Because then if we can plug t into the velocity vector, we can get the speed. How are you going to find the t, the time, for right before impact? Anyone remember that from physics or somewhere else?
What was the question? My kid was yelling at me.
That's all good. How do we figure out what time is right before impact? Like right here, the instant we slam into the ground.
And the x component is 0?
Close. It's going to be the y.
Yeah.
This is going to set y equal to 0, and this is the y of r of t. So if we go to our position function and we set the y component equal to 0, solve that for t. So take whatever's in this red box, right, and set that equal to 0. That'll get you the time right at impact, and it's that we can plug into our velocity, find its magnitude to get its speed. All right, so there's a little bit more about projectile motion. And I would argue that really it's nothing new. It's all stuff you've done before. It's just we're combining it. We're combining it all into just one thing, into this vector valued function, so that we can just go instead of breaking it into pieces. Now, we still have to break it into pieces sometimes, right? Like to find this time, we had to look at just the y component, or same thing with this one, trying to figure out when we're just about to impact. We look at only the y component. But for all the rest of it, we can just treat it as one thing instead of breaking it into components and then putting it together. Instead, we're putting it together first and then going. So it really is one of those, what do they say, 6 of one, half dozen of the other. It's virtually same. It's just in some situations this can be faster. All right, so any questions on this? And hopefully for those of you who have not seen physics, this isn't terribly blowing you away. Just treat it as a math word problem and you'll be good.
So the speed right before impact is when you set the R of t equation, the y component equal to 0.
So y equals 0, and
You
then
solve
plug
for
that
t.
in.
Gotcha. And then you plug it into the velocity.
And into velocity. The acceleration, since acceleration is always constant, you don't have to plug it in there, but in general, you'd also plug it into acceleration.
Gotcha.
Yeah. All right, so let's look at one more like general class, and then I'm going to talk a little bit about Kepler's laws. Let's talk about uniform circular motion, because this is another kind of special motion that we see a lot. So in this case, what's happening is that we are traveling in a circle. But the other important bit, and this is the uniform, is that we have constant velocity. So whatever our velocity is, it's constant. So obviously drawing a picture of this is super easy. There you go. We're moving around in a circle. We need to have a given velocity. So let's say that we're moving with a velocity of v. And let's give it a radius. And we'll go generically a radius of r. But let's kind of approach this the same way. Let's build a position function. After we build a position function, let's find velocity, let's find acceleration. Let's look at tangential acceleration, normal acceleration. We'll do the whole thing. All right. It just dawned on me that maybe I don't want to use V and R. Let's use B for our radius. Go radius B. And for our velocity, instead of V, let's call it U. So that we don't get it confused with the velocity vector. All right, so I'm actually going to start with position. So this position vector, I just need to be going around in a circle. So we already know that going around in a circle, we can just use cosine and sine. I do, however, need to change the magnitude of this by multiplying by that b. So it's going to be that radius times cosine t sine t. So it's going to be b cosine t b sine t. But we still have a bit of an issue. What's the issue with this?
It's two-dimensional.
It is two-dimensional, but we are moving two-dimensionally. If we're going to move in a circle, we can always just assume that we're two-dimensionally. Okay, so direction, that could be a problem, Victor. This one, it's going in a counterclockwise direction. Since I didn't specify, you know, that's okay. We can go ahead and just leave it like that. Well, how about this? Find the velocity. What's the velocity of this?
Negative b sine t, b cosine t.
Okay, so there's our velocity. What's the speed?
To position. No, it's b.
B. Yeah, it's a problem.
It's going to be B. And the
That's no
problem
good.
is, I want to be going with a different velocity. I want a velocity of u. Crap. All right, so something's funky. This doesn't quite work, right? I mean, my position definitely works in terms of giving me where I am, but the problem is it doesn't give me the right speed. So we're going to have to adjust this slightly. And if you look at the initial position function, here are some things I cannot adjust. I cannot adjust the B. That B's got to be B. It's got to be there for me to get my radius.
You said it's constant velocity though.
I did, but it's
So,
not velocity B, it's velocity U.
hmm.
I want to be able to have a different velocity than the radius of the circle. That's really the issue. Like what we have working right here would be fine if, let's say I had a radius of 4 meters and I was going 4 meters per second. But what if the radius is 4 meters and I want to be going 10 meters per second? This is where there's the issue. Well, okay, so again, so B is fixed. I mean, I can't do anything with that. The cosine and the sine, if I change those to sine and cosine or negative cosine, negative sine, all that's going to do is change the direction that I'm going. So the only thing that leaves me that I can adjust is the t. Now, if I adjust the t, so if that's not just t, if it's something else times t, will that change my velocity?
Yes.
Yeah, because from chain rule, when I differentiate whatever the derivative of that stuff, that's going to be coming out here as well. Does it change the magnitude of r?
No.
You're not going to like this answer. The answer to that is maybe. It might. But it won't as long as we adjust these the same way. Right? If those angles, if the things inside cosine and sine are identical, right? So like if this was 2t and that was 2t, magnitude is still b. But if they're different, 2t and 3t, now my magnitude isn't b. So the only place that I can adjust anything is by putting a multiplier in there for cosine, in the cosine and in the sine. So that's what we're going to do. So let me change this. Instead of just t, I'm going to put a c there for right now. So this will be the cosine of ct and the sine of ct. And our goal here really is to figure out what does that c equal. All right, well now let's look at what we get when we differentiate. So now we're going to get a minus bc sine of ct, comma, bc cosine of ct. And so what's its magnitude? What's the magnitude now?
EC?
There we go. That's equal to bc. All right, now I want that to equal my velocity of u, which tells me that u, or c, sorry, has to be u over b. So we're going to have a slight amendment now to r. This is what r really looks like in this case. R is going to be b cosine of u over b times t, and b times the sine of u over b times t. But now we've got it so that the position, but the magnitude of r is always b. So we're always that radius away. And the velocity is going to be u. Always, which is what I need for this guy. So here's the deal. Let me move away a little bit so I can see you a little bit better. All right, so here's the deal with this. The sine and the cosine, that's what makes it so we're going around in a circle. If you want to adjust the speed, you have to put a multiplier on that t. And if you really think about it, that should make sense. Because just take any old, just like cosine by itself. Forget about that it's part of a vector value function, but think about cosine. When you have a multiplier on the t, what does that change?
Phase.
Not phase. Phase would be if there was an add, but vector just put up there, it's the period. Changes the period, changes how often you cycle through. Now the cycling through of the cosine is going all around the circle. And so by putting in a multiplier in here, you're changing how quickly you go around the circle. You change the velocity. So that's what we have to do if we want to have some other weird velocity. But the multiplier is always going to be the velocity you want divided by the radius. Always. All right, so there's our R, which then of course means our V is going to be U, or sorry, minus U times the sine and then U times the cosine. Right, but that was by design, right? We made sure that those things were equal to U with this substitution. But now that we've got that velocity, let's get our acceleration. So if we differentiate one more time, we're going to get minus U squared over B times the cosine of U over BT, and minus U squared over B sine of U over B times T. All right, so there you go. We now have position, velocity, and acceleration for uniform circular motion. And it doesn't matter. You tell me how fast it's going, and you tell me how far away. I just put those numbers in, U and B. I put them in there, and I've got my function. All right, so now let's look at A sub t, A sub n. All right, let's look at that stuff and see how that falls out for the circle. All right. Before I go there, any questions? We kind of okay with that? All right, looks like we're okay. All right, so let's do this. Let's first find a sub t. So a sub t, we want to start with v dotted with a divided by the magnitude of v. So the magnitude of v is u, right? We know that that's just the speed as we're going around, so that's just u. So let's look at v dot a. So I've got them just lined up here. Let's see what happens when we multiply these together. I'm going to get a plus u cubed over b times sine cosine. From this one, I'm going to get a minus u cubed over b sine cosine. And so it turns out that dot product is 0. So by the formula, what we find is that the tangential acceleration is actually 0.
Which is good because it's constant velocity.
Right. This is one of those things we didn't really need to calculate it. This is actually a really good check to make sure that what we did was right. But going in, every single one of us should have been able to go, ooh, a sub t is 0 because I've got constant velocity, or constant speed, I mean. Constant speed means no a sub t. Okay, so then that means a sub n, well, that's going to be the square root of the magnitude of a squared minus 0 squared, which means it's just going to be the magnitude of a. All right, well, let's get the magnitude of a. So the magnitude of a is going to be the square root of this thing squared, u to the 4th over b squared times cosine squared. I'm going to be lazy and not write all the stuff in the cosine because I don't really care.
Just u squared over b, right?
And so then if we do the other one, we get u to the 4th b squared times sine squared, which of course is the square root of u to the 4th over b squared, which is u squared over b. So tangentially, there's none. But normally, centripetally, we get u squared over b. And you do notice that it does point inward because it's the opposite direction of r. Notice the signs are different, minus. So it is pointing towards the center of the circle, which is what we expected. And its magnitude is u squared over b.
And since we did this all generically, this is every time.
Every time. Any uniform circular motion. So for those of you who took your physics, you may remember there was a formula for acceleration for circles that was v squared over r.
Yeah, I do remember that.
Well, this is where it comes from. U squared over b, v squared over, I mean, that's what those are, right? U was our velocity, b was our radius. So most likely you had to just sort of take that on faith back in the day. But now you can see exactly where it comes from this context of talking about just motion in general. This is another reason I love teaching physics, especially the calc-based. I've never taught non-calculus-based physics because I just don't know how to do it. Because to me, this is why physics does what it does. The calculus says it must be. And without the calculus, you do just have to accept it. And I'm not a huge fan of that. Like, for me personally, I don't like just taking things on faith, right? I like to know why. I like to know where they're coming from. And as a teacher, I'm the same. Like, I really don't want to just be like, well, here it is. Because if you guys just accept everything I say as gospel, and I could totally be lying to you. I could be making shit up left and right, and you just would be like, okay, that's not good. The whole point of science is to actually look at things and figure out why and question whether or not processes are correct and all that, right? So if I'm going to help train you guys to be scientists, I need to train you to ask the questions and look for the answers. And here it is. Here's the answer to why in uniform circular motion, A is equal to V squared over R. And also why it's always pointing towards the center of the circle. Two facts that you just sort of, first time you heard them, went, okay, sounds reasonable. Bruce wouldn't lie to me. Kathy wouldn't lie to me. Right, but now you know. Now you know I wasn't lying to you. Now you know Kathy was being upfront. But you have the tools to see it now. Anyway, all right, so there's uniform circular motion. Kind of cool how it all sort of comes back. All right, so the last thing I want to talk about physics-wise, and this will start hopefully addressing the question that Bradley started to ask me that I kind of waved him off on. I want to talk about Kepler's laws of motion. Now, Kepler's laws, these are all about orbiting bodies. Planets going around the sun, moons going around planets, artificial satellites going around the Earth, comets, like whatever. If they're in orbit, they follow Kepler's laws. And there are 3 of them. So let me start by writing them up here and then we'll talk about them. So these are Kepler's laws of, I can put here, orbital motion. Okay, so here's the first one. Orbiting bodies travel in elliptical paths. But there's even a little bit more to this. Not only are they traveling in an elliptical path, but the object that they're orbiting it's located at one of the foci. So I'll give you a second to write that down. All right, so basically, not basically, but here's your picture. So we've got the orbiting object. So let's just, for the sake of it, let's call this the Earth. So since the Earth looks mostly blue from space, I'll be our Earth. Okay, now, ellipses, if you remember them, they've got a center, but then they have 2 foci. Like the way that a focus or an ellipse is defined is it's a set of all points that are whose sum of distances to 2 fixed points is constant. Those 2 fixed points are the foci. But it turns out that the body that we're orbiting, so in this case, the sun, is located at one of the foci. So this is true for all of the planets, all of the dwarf planets, all the asteroids, the comets that are in orbit around the sun. We all do this. There are different ellipses. They have different sizes, right? Their major axes are different lengths. Their eccentricity, how circular they are, right? Ones that are very circular have a eccentricity that's near 0. As they get elongated, that eccentricity goes towards 1, right? So you get different numbers there. There's a way of defining it, basically how stretchy it is. So like cigar-shaped ellipses versus circular-shaped ellipses, different eccentricities. So like the Earth, our circle, our ellipse is fairly circular. It's not a circle. There are times when we are closer to the sun.
January.
Yeah, it's kind of crazy that we are actually closest to the sun in our winter. Go figure, right? The reason that we actually have winter at that time of year is because the Earth is tilted. And so we're tilted away from the sun. Like if the sun is over here during the winter, we're tilted like that. In the summer, we're tilted closer. So like right now, we're kind of at that even point. In fact, that even point happened just a couple of days ago on September 21st, the equinox. Yeah.
So in the summer, everywhere on Earth, wherever you are, yeah, in the summertime, you are furthest away from the sun.
In our summertime.
In the north, in the all of northern hemisphere, all northern hemisphere summertime.
Well, that's why it's better to say like a month, right? Because if you go to Australia, June is still June, right? But
Oh, right. Let's say July.
yeah, but you get my point, right? So like
Yeah.
So if we're going to say July in Australia versus July in the United States, the Earth, of course, is at the same point in the orbit for either one of those, for either one of us. If we're talking to our buddy in Australia, right, the Earth is still the same Earth, right? And in July, we are furthest away from the sun. And then when we come back around over here, this is now January. But obviously, like we get different seasons because January down in Australia is hot. It's their summer. July is cold. It's their winter. But that's because the Earth tilts.
Does that have any effect on southern hemisphere winters being colder than northern hemisphere winters? Does that question make sense?
That does make sense. I actually have no idea about that. I will tell you that one of the big differences, though, between northern hemisphere and southern hemisphere that probably outweighs any difference in distance to the sun is the amount of water. If you look at the southern hemisphere, there's very little land mass relative to the northern hemisphere, right? I mean, you've got Australia, but Australia, because it's so far down, or not Australia, Antarctica, because it's down at the pole, it doesn't really affect things much in terms of weather patterns that way. But there's a huge difference in weather depending upon whether or not air is traveling over water or land. And if you look at a globe, you'll see the northern hemisphere has tons of land, right? Almost all of Asia is northern hemisphere, all of Europe, all of North America, right? Even part of South America is northern hemisphere, part of Africa is northern hemisphere. Southern hemisphere, you've got Antarctica, you've got Australia, you've got the bulk of South America and like not even half of Africa, and most of it's water. And water really helps regulate temperature because of the fact that it's a huge thermal sink. I'm starting to get into thermodynamics terms here, but water has a huge specific heat capacity, so it retains a lot of energy, heat energy, and has a lot to lose. And when it gives it off, it helps moderate temperatures. That's why places like Seattle, you don't get horrible cold Seattle winters. But at that same latitude are places like Minnesota, which if you've ever been to Minnesota in the winter, it's freaking cold, right? But it's because Seattle's got the Pacific Ocean helping regulate the temperature. Same thing, you go further north, like Anchorage, Alaska. Anchorage, Alaska doesn't get iced in. That port is pretty much open year round, and it's high up there. I mean, you're upwards of 60 degrees north, right? You go to that same latitude in the middle of Russia, Siberia, Oh yeah, no, it's horrible. Anyway, so I don't actually know if southern hemisphere's winters are worse than northern hemispheres, and in fact, I would guess not. I'm going to bet that because of all of the water, that most of the southern hemisphere has pretty temperate winters, with the exception of Antarctica. But that was a long way of me saying, and I don't remember, I think that was you, Seamus, who asked it. That's a long way of me, I really don't know. My guess would be that that difference in orbit isn't significant enough for us to notice or for it to affect it. Because it really isn't that different, believe it or not. The distances, I'm trying to remember what aphelion and perihelion are. They're not off by much. It's a very small percentage difference, which is probably a good thing, because otherwise I don't know that life would have been able to form on Earth like it has. You know, that's one of the good things, is that, you know, go to just some point on Earth, there's not a huge change in temperatures that that a living organism would have to deal with. I mean, you might go, yeah, but in the summer it gets to like 80, and in the winter it gets down to 0. That's still not that big of a swing. We're not talking like a couple hundred degrees Fahrenheit or Celsius swap, which is what happens on other planets. Like Mercury's crazy. You go to Mercury, the sun side versus the side that's not in the sun, it's something like 300 degrees C difference. So anyway, point is, we're fairly circular. Now I've forgotten what I was talking about. Something about Kepler. I don't know. Oh, okay, thanks. So Matt just said, that he buys my thesis. I'm just really good at bullshitting. I mean, honestly, I'll keep talking until people go, all right, sounds good, shut up.
I don't know. I could
And
talk
this is when you
about
can
this
type
all
in.
day.
Yeah, what about the Corey?
This is when you type in this is when you actually type in, sounds good, shut up. No, just kidding. But anyway, so that's Kepler's first law. And this actually you can prove using vector valued functions. I'm not going to go through it. I don't feel like reading it to you from the book, because that's pretty much, like, the book goes through it, step by step. But if you just use Newton's law of gravity, and then you apply the vector value function stuff, it turns out that the position function is elliptical, right? And so Kepler was able to prove this first law pretty easily, actually. I mean, if it can be done on like a page or two in a textbook, that's a pretty easy thing to prove, right? I mean, you can imagine. So he was able to prove that one pretty quickly, but this is definitely a fact. I know some people ask me what's at the other focus, and my answer always is, no, nothing. It's just another point that happens to be out there. It's kind of interesting, but it doesn't really have any properties that matter in terms of the orbit. All right, so there's the first law. Okay, now the second two are a little bit more complicated, and this is probably, I'm going to guess, Bradley, that yours is related to either the second one, but probably the third one. But the second one says that the radial vector sweeps out an area of equal size over the same time period. Okay, so let me kind of explain what I mean here. But the radial vector, and what I mean here by the radial vector So this is going to be between the two bodies. So like with the Earth and the Sun, it's the line that connects the Sun and the Earth or whatever. So let's say that this is our body that we're orbiting. Let me keep the color coding here. So if we were to start the clock as we're traveling from one point on our orbit to the next, you think about those radial vectors, you get all the radial vectors that are somewhere in between along the way, and that shades in an area. All right, well, if you were to look at the same time period, okay, so let's just call this a delta t. If we were to do the same time period somewhere else on that path, so let's say we're going here to there, and again, it gives us a shaded area. Those two areas are equal. All right, so that's what this one said. But yeah, go ahead, Bradley.
So it speeds up.
Yep. That's actually a direct consequence of this. Where is it going to be traveling fastest?
Closer.
At the edges.
Yeah.
So it's going to travel faster when it's closer to the body that it's orbiting. Right? Because if it's really far away, let's think about like when we're really far out here, because that length is so great, we're going to sweep through a big area in a short amount of time. If the distance to that body is short, to get an equivalent area, we're going to have to go a longer period of time. Right? But if those times are the same, that means we have to have different speeds. And so that is really the consequence of this. Right? The result of this is that the body travels faster when closer to the, I'm going to call it sun, but it could be the planet that the moon's going around or whatever. All right, now we just had a really good example of this not that long ago. You guys remember when that comet was here like a month ago? Yeah, so just the past couple of months, there was a comet, Comet Neowise. I don't know if any of you guys went out and saw it, but I, of course, I went out and looked at it. But it was only visible for a short amount of time, right? It was only visible for like a week. And that meant that it basically, on its orbit, it traveled if the Earth is here, let's say, it traveled this chunk in a week. So then when it's far, far away, in a week, it would do similar area. Well, a week out here is going to be a super short amount of time. And so we definitely see this, like Halley's Comet's a great example. That's probably the most famous comet in terms of, because it's been seen historically, it's been written down in historical record many, many times over history. It does come regularly every 76 years. So in a lifespan, most people see it at some point. Some people are able to see it twice. Right, so it's a really famous one, but it takes 76 years for it to complete its orbit. It's only visible from Earth, again, for like a week, 2 weeks. So just think about that, how much faster it's going when it's near the sun versus when it's far away.
All right, so I think I know, or at least I have an idea on why this is the case.
Okay, why is this? Why
Because
do you
the
think?
sun is so massive, it bends space around it, right? It warps space. So if we were to pretend like on a piece of paper, like a big fat
A
marble in it,
bit.
it would bend the paper. And as you come towards the sun, like you're rolling faster down. You know what I mean? Like a hill. And
Yep.
then you're still moving, so you come back out, and then it slows down a little bit as you come away. And then you just keep doing it.
That's a great way to think about it. And I don't know if you guys have seen, like on YouTube, like the marble racing leagues and the marble Olympics and things like that. If you haven't seen these, go check them out. They're kind of fun. The announcer guy is awesome. If you like sports, you'll really appreciate it. But one of the events they do is a thing where they drop into a funnel and they just kind of spin around. And if you watch them, if they don't approach that thing in a circle, you'll see exactly what Bradley was saying. As it comes in towards that hole, it speeds up and kind of gets whipped around and then slows down, comes back out, speeds up, gets whipped around. It's the same reason that you can do that gravitational slingshot when we send probes like to Jupiter, but we send it past Venus first. Always seems like kind of a weird thing, right? It's like, you're going the wrong way. No, we're going to get a boost. But yeah, that is exactly what's going on. Now, Kepler didn't know about distortions of space-time. That wasn't even a thought back then. I mean, that's really new, right? That came about during Einstein's time, which is just slightly over 100 years ago. Kepler was more, I think he was 1700s, maybe 16. I'm not entirely sure. But he didn't have the idea behind it, but it is exactly what you're talking about. Think about just acceleration. We know gravitational acceleration, the force due to gravity, it's inversely proportional with the square of distance, right? It's an inverse square law. And so when we've got an object that's in here, it's getting much more acceleration. And yes, we can't just go immediately to the v squared over r because it's not circular, but it's kind of related. Well, if you increase that acceleration, you're increasing your v and decreasing your r, and in tandem, it causes an increase in your velocity. So it definitely just falls out from the math, no doubt about it. And it does make sense if you think about the sun or whatever orbiting body as warping space-time in the way that we see, like with a funnel with marbles and stuff like that. All right, so there's law number 2. It's kind of cool. And again, you can easily prove it. All right, so then there's the third one. And it's the third one that probably is the one that you probably have questions on, Bradley. And it goes like this. If you were to look at the ratio of the periods of 2 planets, right? So we got this orbiting going on, but you've got 2 planets. It's actually equal to the ratios of the cubes of the semi-major axes. What? Okay, so basically here are 2 planets that are orbiting the sun. So here's planet number 1. Now let's go planet number 2. And so we'll put the sun at the focus of both of these things. All right, so look at from the center out to here. That's the semi-major axis. Major axis is the long way across. Semi-major means half, semi is half. right? So there's a semi-major axis. For this other one, the semi-major axis would be this. So I'm going to call these, say, A1 and A2. Okay, so what we're going to do is we're going to look at the ratio of the cubes of these. All right, so A1 cubed over A2 cubed. Now, each of these also has a length of time that it takes to go all the way around, so called an orbital time, but it's a period. So if this object takes to go around its path, big T1, and this other one for it to go around its path takes big T2, this ratio is the same as T1 squared over T2 squared. So you'll sometimes see it written like this. You notice I didn't try putting it into words because writing it out is kind of a pain. Right? But sometimes you'll also see it if I kind of switch things around. So I've got the ones together and the twos together. I've got A1 cubed over T1 squared is equal to A2 cubed over A2 squared, or sorry, T2 squared. And so since these have the same form, and we don't necessarily want to be talking about other planets or things like that, sometimes what we'll do, you'll just see this written as A cubed over T squared equals K, where K is a constant value. And that K, it depends upon the body that you're orbiting. So like if we're going to talk about planets orbiting the sun, that will give us a specific K. Like for the Earth's, like, because we can pretty much do this for Earth. The T is 1 year, right? It takes us 1 year to go around. So 365 days, like, well, 365.24 or something or other, right? But 365. The A, well, it's that distance from the sun to the Earth. Now, we're not circular, right? We're not exactly circular, but roughly. So that's about 93 million miles. So we could get a ballpark for the K by taking our, we might want to make it into nice units like meters per second or something like that, kilometers per hour. Yeah. I would definitely try not to use miles and years and things like that. But basically, you take your 93 million miles, cube it, divide by your 365 days squared. That's the K value. That then would translate to all the other planets. So if we were able to then, say, calculate how long it takes Jupiter to complete a cycle, we could use the K that we calculated for Earth, the time for Jupiter, and then use that to figure out roughly how far away Jupiter is from the sun. And believe it or not, that is what they did back then. When they first started getting ballpark idea for how far away Jupiter, Saturn, you know, all those orbits were, they used periods and Kepler's third law to do so. So somebody started saying something. Sorry, I kept talking on you.
Well, I was just saying far. That's Jupiter's orbit from the sun. Far.
Oh, yes. But not as far as Saturn's. So, but yeah, okay. So this then is the third law, which just relates periods and distances. Again, you can prove all of these just by using vector valued functions. So I'm not going to, like I said, I'm not going to prove them to you, but you can take them for what they are. which are pretty cool and interesting. And the only way they came about was by looking at vector value function. And I just realized that I'm like way over time. I just looked at the clock and I'm like, oh crap. So I apologize for running long. I guess we're not going to get to multiple integration today, but that's okay. Because this is cool stuff, and I want you to see that there is a reason for doing what we're doing. I know by this point, most of you know, right? You don't get to the second year calculus without having some appreciation. But the more of this you see, the better. Gives you reason to actually want to do it, right? Okay, so again, I apologize for running a little long. It happens sometimes, especially when you get me talking about something I really like astronomy. So what we'll do on Wednesday, because I also realized that we didn't talk about the quiz at all. I still need to get that graded, but I'll have those graded by Wednesday. We'll talk about the quiz, and then we'll move on to multiple integration. Don't forget to get in there and work on the homework tonight. I think it's only one set since I moved this one, but you can definitely get in there and do most of this now. And in fact, I would recommend you start working on that sooner than later, because there will be other things that are coming up on the next week homeworks as well. Anyway, so with that, I'm going to go ahead and pause our recording.